Uh, yeah, my screen is visible, no?
Yes, yes.
Yeah, okay. So when we receive our signal, no, so this is how it looks. So y bar equals h bar into s bar plus n bar. So where y is our received signal, h is the channel coefficient, and s is some unknown signal, and n is the noise. So now we want to get only the transmitted signal from this. So for this, what we do is we have to estimate this channel coefficient first. To do this, we should be this is unknown, right? So h bar is unknown. We don't know how the channel reacts. And another thing is we don't know this as well. So how this signal is coming in. So what we do is we do a channel estimation for this using the timing sequence. As you might be knowing that at transmitter side, I'll show you how the packet will be there. Okay. Uh, is my slide visible?
Yes, sir.
Yes, sir.
Okay. Uh, it's not moving. Let's see. Uh, I think presentation is not opening properly. 1 minute. Let me reshare my screen. So, sorry for this disturbance. I think I'm not able to share my screen. I will log out and log in once. Okay.
Okay, okay.
Yeah. Yeah, sorry for this. Yes. Yeah.
We can see the screen now. Yeah, PPT is also visible.
Okay. Yeah. Thank you. Okay. So as you can see, while transmitter only, we have added as God bits, God symbols, sync symbols, training symbols, data symbols, and God symbols. So Raghavendra might have told the importance of all of this. So this training symbol is very much important at receiver side during channel estimation and equalization. So the training symbols which we are sending at transmitter side will be used at the receiver here. So here, as we know that the H is unknown and S is unknown, this we will not be able to decode what's inside. So only one unknown is there. We might have determined the solution. But for this, what we do is we take the training sequence which we have transmitted to the transmitter and received here. Here, the training sequence is known for both transmitter and receiver. So we will call it as T with a number of bits. So this is known for both transmitter and receiver. By this, we can say that y bar equals where h bar will be our unknown and tn will be our training sequence, which is known at both transmitter and receiver. And now I will add this noise. And this noise can be ignored right now because we have taken care of this at starting only the pulse shaping filter where our SNR will be very high so that this can be ignored. So we are left out with y bar plus h bar into tn where it will be a training sequence. So now what we will do is we will just estimate this h by doing an least square estimation. So where we'll be determining our h bar using this training sequence. So using that will be least square estimation is a one technique where we can determine the h bar approximately or exact value of h bar. So for this, what we will do is we will create a matrix. So matrix calculus is very much easy to calculate the big number of data. So what I will do is I will create a matrix uh, which is having of L. I will tell the importance of L. Y L plus 1 so on unto nt minus 1, where NTs are the number of training bits that we have added, which is known for us, equals the training bits. It goes until t of 0. This is t of nt minus 1 t of nt minus 1 and L. And this will be our response. Yeah. Okay, so this is how least square estimation can be done using the receive signal and the training sequence. So this training sequence, this matrix is known for us. So this whole thing is known for us, and this is the received signal what we are getting, and this is the unknown signal. Like we will be estimating using this thing. So this is the transmit bits which is known before, and the received signal which we are receiving from the USRT, and this is what we will be estimating. So usually this L, what we are seeing here, no. So this is nothing but the channel length. So depending upon the channel behavior, we will be estimating, we will interpret this L. So for example, if we consider like this is transmitter and this is receiver. Okay, so this will be transmitting. So there might be path loss and some reflections might occur. So let me consider this as some door, and this is something car. Okay, so this is the line of sight. This will be the line of sight, and this will be the reflected path. So now we can see that there are the receiver will be having the line of sight signal also, and some reflected signal with some delay. So to overcome this, we will be interpreting like how much the reflection is happening. Usually, what after many time of experiment, we found out that L is around 2 or 3, because even though there is many reflections like other devices, like there can be a chair, there can be some wall reflecting the signal, uh, the the delay is not very much. Like the delays, when we observe, no, there is very less delay between the virgin signal and the reflected signal. So we ignore many signals and just consider some of the signal which is having more significant effect on the received signal. So this is what we have got, and this is how the estimation happens. So after we get the what the estimated value, what we do is uh, continue here. Okay. So what we do is we do we construct. Sorry, what? Hmm. After estimating this uh, H, what we'll be doing is we'll do an H inverse, because we have to remove this H effect inside our in the received signal. So to do that, we'll be doing an H inverse of the estimated thing. So now the estimated, yeah, the estimated coefficients will consider it as F equals H. uh, F equals H, and we'll be doing an inverse of it. So that H into H inverse will give us the impulse response of the signal. So what we do is, the next step is we convolve our the estimated F, that is H inverse, with that of the received signal. Fine.
Ajay,
Yes, ma'am.
yeah, like can we spend time with the simulations or the lab VI file?
Yes, ma'am. Because before going to that, you should be knowing the concept how it is built. So I'm trying to
Okay,
explain.
okay. Because I think PPTs can help us to understand the connectivity.
Okay. Okay.
I think the participants would like and appreciate more if we can elaborate the simulation part of it.
Yeah, sure, ma'am. I will go
Okay,
through that. Yes, ma'am. So I was just giving a brief about how we have built, so how
correct,
it
correct,
works. So
correct.
if we know that, that can be easily understood.
Yes.
That's why I'm trying to convey this. Yes. Okay. So I will try to
No, we
after do.
can be a bit faster on the side.
Okay. Okay,
Okay.
ma'am.
Yeah,
Yeah.
that can be better. Rather skipping it, we can go a bit faster on
Okay, ma'am.
this. Yes, thank you.
Yeah. Okay. As we know, so this is Y bar, H bar, as well as I've explained before, and then we'll be doing we'll estimating this H, and then there is an toy-plate matrix. So I forgot to tell about that. So we can say that the estimated channel might not be a perfect square matrix. So for that, what we do is we do a toy-plate matrix estimation. So so this is what we have done, right? So this is a H, what we have estimated. But the received signal would have been more than that of the estimated channel. So when we do that, you will be getting an impulse response. So after doing this, you'll be getting an impulse response, something like this. It keeps on going. Here also, so zeros will be there. So this is the point where we'll get a perfect estimation of the channel. So how it behaves, we can determine that. So using this response, we'll be convolving the estimated channel with that of the original signal. So I will be showing it in slides. So this is how it looks. So this is the dotlet matrix, how we construct the dotlet matrix. And then the convolutional we do, and we get the impulse response, as I told. And we get the original signal from the received signal. So this is how the channel equalization and channel estimation works. So now I will be showing you the demonstration of the SISO transreceiver, both transmitter and receiver data. Before that, I will show how the receiver code looks like. Okay, so this is the front panel. So this is how it looks. Similar to that of transmitter, we will be giving the USRP device name, the IQ rate, carrier frequency, gain, and active antenna, and this data bits per packet. The conventional coding, like channel coding, whichever you want, like conventional coding, Hamming coding, or custom coding can also be done in this. And this is QPSK, BPSK, PSK. You can select whichever uh, modulation scheme you want. And then this is another part where this frame structures will be, like as I told, a transmitter also will be knowing that the number of god bits we are adding, sync symbols and training symbols, which is not prior to us. So that will be giving the information here, and then the channel parameters. So as I told, there are we are doing channel estimation so that the bits that we have missed, or ISI, if something ISI occurs in the received signal, it can be overcome using the channel estimation technique. So for that, there are some basic parameters that should be given. That is channel length, equalized length, and equalized delay. And here we can see the filter parameter, that is 0.5, which is similar to that of transmitter pulse shaping. In transmitter set pulse shaping filter alpha data, and the filter length. So these are the basic informations that should be basic data that should be given to the receiver, and the constellation diagram can be seen, and eye diagram, equalized constellation diagram, and the eye diagram of the equalized data, and IQ waveform. So this is how the front panel looks, and I will be going through the block diagram right now. So before going to block diagram, I will show how the USRP can act as a receiver. So I think Raghavendra would have told how USRP would act as transmitter and what are the main VIs, sub VIs that are required. Now I will be showing you how the receiver works. Like the USRP can act as receiver. For that, so now this is the block diagram. So here, if you want the USRP to act as a receiver, we go to instruments, instrument drivers, and there inside NIUSRP, we can see there is RX and TX. Now I'll be going through RX. So in TX, you might have seen there are four VIs. So to act the USRP to act as a transmitter. Here we'll be using six sub VIs to make sure that the USRP work as a receiver. So first one is open session, second is configure, third one is initiate, fourth one is fetch data, fifth one is abort, and the last one is close session. So these are the basic blocks that are required for USRP to act as a receiver. So as Raghavana might have told, the open session is used to make that USRP to work for this program only, so that it doesn't interact with other programs and transmit that data. It will be confined only to this uh, code unless it has been closed, like closed session is there. No? Until that, it will be running in this program only. So next is the configure signal. So similar to that of transmitter, the configure signals are there in receiver as well. So this is initiate USRP. So this is used because, as you know, antennas are passive devices. So the receiver might be keep on receiving the signal, some unnecessary signals it might have been receiving. So to overcome that, we use USRP initiate. So this happens only when you want to process the data. Instead of receiving some random signals, we can initiate the USRP to work only when the you are transmitting or you want to receive the data and process the data that has been received. So that's why USRP initiate we do, and then it's RX data, right, like whatever the signals we are receiving, right, so that will be converted into digital signals so that it can be used for further processing of data. And next is the abort. So whenever we start receiving, no, there is an register inside the USRP, so that it stores the data whichever it is receiving inside some memory block. So whenever we abort or stop the program suddenly, there might be a chance that the memory might be having the previous data, whatever it has processed. So to make sure that the queue, that register which are there inside USRP get emptied, we use abort function so that every bits that are inside the register get dequeued and only blank registers are there. And then we close the session so that the other programs can use the USRP for their purpose. So for this, basically, we should be connecting all the reference wires for each block, and then the error wires. Have created already the inputs and the outputs that needs to be given to this. So first, as you might have seen in transmitter also, first what we do is we give the device name, and then we configure the signals like the IQ waveform, what's the IQ rate, what's the carrier frequency that we want, and the gain of the received signal. If you want to increase the gain of the received signal, we can do that using this gain control. And then this is the coast carrier frequency. I think Raghavana meta tool, again I will tell about this. So this coast carrier coast data what we see, no, so this is nothing but the USRP limits. Like if we are transmitting beyond the USRP band, like if the USRP is working from 1 gigahertz to 6 gigahertz and we are giving 8 gigahertz, the USRP automatically down converts the signal to 6 gigahertz. So it will be transmitting at 6 gigahertz signal instead of 8 gigahertz. So that can be seen through this. So this is how it works. So carrier gain also, it takes only the um, reference given gain. Like if we give similar to that of carrier what I told, if we give the gain beyond 30 or 40, it will goes back to 15. So this, it depends upon the USRP capability. So if it can go, some USRP can go up to 10 dBm, 20 dBm, and some USRP can go up to 2 to 4 dBm, like that. So this can be seen through this. So this is how the complete um, block diagram looks like the VI looks like for the USRP to act as a receiver. And another main thing is we'll be keeping the USRP data, fetch RX data inside the while loop, because we want to receive the data continuously, right? So for that we'll be keeping our RX data, fetch RX data inside the while loop, so that the USRP keeps on retrieving the data from the transmitted signal. So this is one thing. So this is how the basic block diagram looks like. So I think everyone is clear on this.
Yes, Ajay.
Okay, yeah. Okay, so now I will be going through the code of receiver block. So this is front panel. So this is the block diagram. As you can see, initially we are doing an ESRP open session and configure the signal. So Raghavendra might have told about the producer consumer loop. So similarly, we have used the same architecture in a receiver as well. So this is the main loop, and this is digital signal processing loop. And another one is decoding packet loop. So here what we do first is, it is a state diagram where the initial state is calculated frame size. So initially we'll be calculating the frame, like how many God bits are there, how many sync bits are there, and the training sequence. Everything, the information will be given by us, so that the receiver know how much data that it needs to retrieve from the transmitted signal, and then we initiate the signal at that time. After that, the next state is receive data. In received data, depending upon the number of samples that we calculate in previous state, the USRP retrieves the data according to that, and we can see the constellation diagram in front panel, which I'll be showing in some time. So this is how the first loop works. So that the everything happens parallel, like the USRP keeps on receiving the data, and then the process happens simultaneously, like digital signal processing happens simultaneously. So this is the receiver digital signal processing loop, where the received data will be processed. So as I have told the basic blocks, first we do is match filtering, next we do is symbol timing recovery, and then we do is downsampling, and then detect frames. So there is a case structure where I have told the packet passing what we do, right? So this happens here. The previous data, the previous frame, if there is like off frame we are receiving at one time, and another off it's in next time slot. So it will store the present time slot data, and it will wait for the next state to come in. If the next state has come in, is there, then only it will become true, and it will go to packet stitching process. So here the packet stitching happens, and then we generate the channel coefficients, and we do equalization of data, and we convert the received signal with that of the channel coefficient, so that we get our data properly. And then at last we do is symbol to bits conversion. So this whole process is very much important in SISO receiver block, so that every bits are decoded properly. So next loop is decoding loop. So as this process takes more time, we created another loop so that the decoding happens parallelly. So the first state is wait for buffer to fill. So this is very much important. Like as you might be knowing, in YouTube and all, initially the video will not load. Like it will take some time to load. Like so that is called as a buffer. So similar to that, what we do here is we wait for the buffer to fill. Like after this signal, signal is processed, we give out the data to the next loop, where it waits for some initial buffer what we give. Like at present we have given 10. So until the 10 packets come in, it wait in this state only. Like it will store the 10 packets data, and if the 10 packets data, like it has received more than 10 packets, it will go to next state, where the sorting happens. We have placed this sort packet because there might be a chance that we receive a third packet before the second packet, or fifth packet before fourth packet. So that might happen, right? So to make sure that that doesn't happen, we sort the packets whatever we get. So for example, if we get from if we get 1 5 4 3 2 1, like that, it will get sorted in ascending order, like 1 2 3 4 packet will get sorted out, and then it goes to the next state where we decode the packets. Here normal this channel decoding happens, and after that we will be doing the bits to text conversion, where the data will keep on decoding according to the process data. So this how it works is, so first we have received 10 packets. So first it goes to wait for buffer. After the 10 packets has been received from this loop, it goes to next state where sorting happens. After sorting, it goes to this loop and the 10 packets get decoded. But the packets that we have transmitted is around 30 packets. Uh, so what it does is, again it will, after the decoding 10 packets, it will store in its memory, and then it will again go for wait for buffer. In this, again it will wait for another 10 packets to come in, and then it will go to sort packets, again it will go to decode packets. From this we can see that at last we can say that we'll be having all 30 packets at a time. Instead of, if we wait for all 30 packets to come in, it will take more time, so that user might not experience like the user might feel like some delay is there in the receiver, in the received data. So to overcome that, we are using this buffer mechanism. So this is how the receiver code has been designed. Is there any doubt in this? Hello.
No, no, Ajay, no.
Okay. If this is clear, I will show you how the transceiver works. So now this is a receiver front panel, and I will be taking out the transmitter front panel. So now I am transmitting at 200 kilo accurate and 1000 bits per packet. So I will run this code. So it's transmitting. So we can confirm that by seeing this constellation diagram, so that it's transmitting. And next I will